Hi everyone. We present MoCapAnything, a unified system for 3D motion capture and retargeting that works for arbitrary skeletons, taking only a monocular RGB video as input. Motion capture today is essentially locked. Methods like HMR or Vibe work great, but only for the SMPL human template. For animals, small handles a handful of quadrupeds. Category-agnostic 2D keypoint methods like Cape skip 3D entirely. So when a creator needs motion for a robot, a mascot, or a crab, anything outside these fixed templates, they fall back to manual retargeting. We ask a simple question. Can one model capture motion for any rigged 3D asset from a single monocular video? We formalize this as category-agnostic motion capture, or CAMoCap. The inputs are two things: a monocular RGB video and a rigged 3D asset consisting of a mesh, a skeleton, and reference images. The output is per frame joint rotations on the asset's own rig, directly animation-ready as BVH. Note, when the asset matches the subject in the video, this is motion capture. When they differ, this naturally becomes retargeting. 3 challenges sit in the way: how to represent motion robustly across rigs, how to inject reference rig information into prediction, and how to bridge dense RGB features and sparse joint space queries. Our benchmark is TrueBones Zoo, with over 1,000 standardized clips. MoCapAnything is a reference-guided factorized framework. The reference prompt encoder turns the rig, the skeleton, mesh, and image into per-joint queries. The video feature extractor combines frozen DNOV2 tokens with point tokens sampled from a recovered 4D mesh sequence. The unified motion decoder uses temporal cross-attention to predict 3D joint trajectories. Finally, constraint-aware inverse kinematics converts those trajectories into rotation-based animation, respecting the asset's own bone lengths and joint limits. 3 design choices make this work. First, joint queries from the rig. We use a graph MHA over skeleton topology, then cross-attend to sampled mesh points and DGenOV2 image tokens. The result is a per-joint query that supports any joint count via a simple binary mask. Break time equals 400 ms/second, mesh as a bridge modality. Pure RGB struggles to localize joints in 3D, especially under occlusion. So we lift each frame to a 4D deforming mesh using a pre-trained image to 3D model and sample points from it. These geometric tokens carry shape and topology cues that close the gap between RGB and joint space. Break time equals 400 ms/third, trajectories first, then IK. We predict 3D keypoints supervised by a masked L2 loss, then run a 2-stage IK. Closed-form initialization plus iterative numerical refinement. It is optimization-based, not differentiable, but it enforces hierarchy, bone length, and joint limits. On the TrueBones Zoo test split, 60 sequences across seen, rare, and unseen species, MoCapAnything cuts MPJP to roughly 1 centimeter, while the strongest baseline GLOT sits at 3 to 7. On unseen species, we are over 4 times better. The modality ablation confirms what the design predicts. Removing the mesh stream hurts the most, especially on rare and unseen species. Removing the image stream is the next biggest drop. The graph MHA matters, but less. This validates the mesh as the key bridge modality, and the value of pulling all 3 signals, skeleton, mesh, and image, into the same encoder. Now a quick look at qualitative results. The video shows in-the-wild motion capture and cross-species retargeting across very different rigs. To summarize, we introduced CAMoCap as a new task formulation. We proposed MoCapAnything, which factorizes the problem into keypoint trajectories plus IK and uses the mesh as a bridge modality. We released the TrueBones Zoo benchmark, and we showed strong in-domain accuracy, wild video generalization, and non-trivial cross-species retargeting. Limitations: we depend on the image to 3D model, predict camera space only, and assume the rig is known. Code and project page are linked. Thank you.